Okay, Chapter 3, Section 3, Derivatives of Products and Quotients. So let's say the following problem is given. F of x is equal to x cubed times x squared plus 1, and we're asked to find the first derivative of this function. Okay, so if we want to find this derivative, the first thing that might pop in your head is why not distribute, simplify, combine, reduce our function first and then apply the derivative? And that would be absolutely the correct instinct. So let's do that. The first derivative is going to be equal to the derivative with respect to x of this function, x cubed times x squared plus 1. Right? Okay, so let's go ahead and take care of this multiplication first and distribute and distribute. And so we would get that the first derivative is equal to x to the power of 3 plus 2 plus x to the power of 3, or that this is the derivative with respect to x of x to the 5th power plus x to the 3rd power. Good. So that's the first derivative. And now we have a derivative of something that we can easily do based on the rules we already know. We know that if we have terms being separated by additions or subtractions, we can separate it. So this would become the derivative with respect to x of x to the 5th power plus the derivative with respect to x of x to the 3rd power, like that. And now the power rule tells us that this derivative is really easy. It's going to be 5 times x to the power of 5 minus 1 plus 3 times x to the power of 3 minus 1, which means that our derivative is going to be equal to 5x to the power of 4 plus 3x to the power of 2. This is absolutely the correct answer. Okay, so this is definitely the correct answer. Given that this is our given function, f of x equals to x cubed times x squared plus 1, we can follow this process. We can rely on some of the theorems we've already learned, some of the rules we already know, and we can definitely get the correct answer. So the derivative with respect to x of this function is 5x to the 4th power plus 3x squared. Okay, but here's the goal that we're trying to accomplish. Notice that the original function given is a multiplication of what could be thought of as two separate functions. We could think of this as x cubed times x squared plus 1. So x cubed could be thought of its own function, and then x squared plus 1 could be thought of as its own function. So what we would like to do is develop a process or a rule that allows us to take the derivative of a multiplication of functions without first simplifying it, without first distributing it and turning it into something that fits this form of polynomial. Okay, so we want to figure out how we can do that. The first idea I think anybody would have is the following, and I'm going to warn you, this is the wrong way to do it, but I'm going to show you what I think almost everyone tries to do, but keep in mind this is definitely the wrong way to do it. So here's what a lot of people think we should be allowed to do. In a nice, perfect world, this would work because it makes sense. Kind of like when you add fractions, you know, we have like 1 over 2 plus 1 over 3, and you're like, in a perfect world, this would just be 1 over 5 because it's easy. Yeah, it's easy. It makes sense. But it's wrong, right? That's not how adding fractions work. And in the same style, what I'm about to do is definitely wrong. It's not the way you do it. But I'm covering it because it's important to point out what you're not allowed to do. Okay, so here's what a lot of people think. If we have the derivative with respect to x of x cubed times x squared plus 1, a lot of people would like to take the derivative with respect to x of the first one times the derivative with respect to x of the second one. It seems to make sense, right? Why don't you just take derivatives of each one separately and then multiply it? Okay, well, let's explore what happens in that case. When we take the derivative of the first one, this is a nice power rule. So this becomes 3x to the power of 3 minus 1. That takes care of this. And now this is a nice polynomial. We know we can separate it into pieces, and we know that the derivative of 1 is 0. So we know that this is going to end up being 2 times x to the power of 2 minus 1. Simplifying that, we would get 3x squared times, and then this is 2x to the power of 1, right? On the left-hand side, everything stays the same. And then, well, this is a multiplication, so we can multiply these and end up with 6x to the power of 3. Okay, so if we followed this rule, which we just kind of instinctively assumed would be correct, because in other areas of math, this kind of thinking works. Just being lazy here, but on the left-hand side, this is the same. Coming down on the right-hand side, we're saying equals this, equal this. So finally, we arrived at this statement down here. The derivative with respect to x of the product of x cubed times x squared plus 1 is equal to 6x cubed, based on this idea that we maybe instinctively think might be true, but in fact it is wrong, right? And it's wrong, if nothing else, because it doesn't equal the thing we already know is true, right? This follows solid mathematical thinking. There is no assumptions here. We distribute. We know this right here, this distribution is definitely equal to this. And we've already established that when we have a polynomial like this, we can separate it into pieces. And we've already established that these rules for derivatives are true. So we should feel really comfortable stating that this is definitely the correct derivative. So just based on that, I must assume this must be wrong, right? We made an assumption here. Assume that if we want to take the derivative of a multiplication, that we can just take the derivative of each one separately and then multiply their answers. And now we know that that is a bad assumption, not true, doesn't work that way. So don't make that mistake. So if you were given something like this one, you would probably just want to do it this way. This wasn't that bad. In fact, I probably wrote too many steps here just to make sure you guys are following, but you could probably do this in less steps. It's quick, it's easy, it's no problem. But very, very soon, we will be working with functions that can be thought of as a multiplication, but actually multiplying them would take a lot of work, a lot of time, and they might not even be, something we could do. So we got to come up with a way to multiply them. Okay, so let's just jump to what that rule is. How do you multiply, find the derivative of a multiplication of functions? Okay, so this is called the product rule. This is the boxed up rule provided for you by your author. If f and g are both differentiable functions, then the derivative with respect to x of the product of f of x times g of x equals to, and then this little formula. It's going to be f of x times the derivative with respect to x of g of x plus g of x times the derivative with respect to x of f of x. Okay, I'm not going to bother proving it. The proof is a little bit hard and difficult to visualize, and I'm not sure that there's really that much value to it right now. But your book provides, a quick little overview of the proof. If you want to take a look at it there, that's fine. If you want to come talk to me about it and go over it or something like that, I'd be glad to do that. But I just don't think that there's that much value to me spending an hour walking through that whole proof just to convince you this is true. Hopefully you trust me that this is true. So let's just rather examine this, make sure we understand it, and then apply it, use it, love it, and move on with our lives. Okay, so another popular notation for this is to say the following. If we have, remember we have a lot of different notations in calculus, so we could say this, f times g prime. Remember that notation, meaning that this is the derivative? The derivative of this multiplication is equal to f times g prime plus g times f prime. Okay, so the order doesn't matter. In other words, you can easily also do something like this. You could say that it's equal to g times f prime plus f times g prime, right? Same thing. And also the order in which you write these doesn't matter. So this could also be written as f prime times g plus g prime times f, right? All of these things are all true. They all equal this. So the pattern, right? The pattern is what's important. And the pattern is as follows. If we have a product of two functions, or if you're given one function and you can identify that you can think of it as a multiplication of two functions, as I did in the earlier example. So if you can identify it as a multiplication of two functions and you want to find the derivative, what we do is take turns taking derivatives, right? So we got to multiply the f function times the derivative of the g function, plus, now leave the g function alone, and multiply it times the derivative of the f function, right? So we kind of take turns with it. That's what this pattern is telling us. And then we got to add them together. Good? Okay. This reminds me a little bit of when we learned to multiply binomials, for example. So remember that if we had x plus 1 times y plus 2, when you first encounter this, a lot of people want to do something. Well, let's not make this a 1 just to really see where it comes from. Let's make this like a 3. If we had x plus 3 times y plus 2, and we want to multiply these, a very common thing I think people want to do is to say, well, why don't we multiply the letters together, the variables, and then the numbers together, and then we'll add them, right? So a very common mistake is for people to think that this is the answer, right? Again, let me put a giant thing here. That's not true, but it feels true, right? We want to multiply the letters, multiply the numbers, and there you go. It's xy times, and then plus 3 times 2. Okay, so you kind of want to do that. But, of course, we learn, no, it's actually more complicated than that. And one way to explain that complication is to think about multiplication tiles. I don't know if this is how you learned it. But multiplication tiles look like this, where we have in this direction, we'll say that this is the y. So we'll say from there to there, this is y. From there to there, that's 2. And then in this direction, we'll say that from there to there, that's the unknown x. And from there to there, that's 3. So that together, this whole distance is the distance x plus 3. And then together, this whole distance is y plus 2. So when we multiply them, it'll be the area of the entire thing. But of course, we can also see that the area of the entire thing can be subdivided into little pieces, where this piece here is xy, this piece is 3y, this piece is 3 times 2, and this piece is 2 times x. So we learned very quickly that when you want to multiply these two binomials, it's actually the sum of all 4 of these things, which I think comes to a great surprise to most of us when we first see it. And like, what? How does it turn into this really complicated thing? So it's a little in this style. And if you look at the proof that's in your book, this is how the proof proceeds. They kind of create this sort of a table, and they kind of expand it all out. If you want to look at your book, keep in mind that in your book, instead of this being just a simple y, this will be one of the functions. So in this direction, you'll have something that's f of x. And then in this direction, you'll have g of x. And then you'll have a tile, and you have dy. Okay, so it goes on and on. I'm not going to go deep into that, but you can look in your book to see that. But my only point here is it gets complicated. When you grow in one direction, you're really growing in a two-dimensional space, and you have to think of the rest. And that's why the multiplication of these two functions is not as simple as just taking the derivative of, the derivative of a multiplication of these two functions is not as simple as multiplying the two derivatives together. It's a more complicated setting, and this is what it is. Okay, so take the derivative of each one one at a time and then add them together. That's what it is. Okay, so let's jump into an example. So for example, let's say that we had f of x is equal to, well, let's do the very first one we did. We already know the answer, so we can confirm with it and make sure that our newfound method matches what we think is the correct answer. So let's say that this is the given function and we're asked to find f prime of x, right? Okay, so we follow our product rule. So we're going to think of one of them. So think of this as one function, and we're going to think of this as another function, and they're being multiplied together. Good. So just for the sake of labeling, let's call this g of x, and let's call this, I don't know, w of x. Right? So this is really the same thing as saying that my function f of x is equal to g of x times w of x. Okay, and so following the product rule, I know that the derivative is going to be equal to, leave the first function alone, times derivative of the second function, plus, well, now leave the second function alone, times derivative of the first function. Good. Okay, so now let's go ahead and plug it in here. So that means that g prime of x is going to be equal to that first one, so leave the first one alone, x cubed, times the derivative with respect to x of that second one, so times d dx of x squared plus 1. Plus, now leave the second function alone, okay, so we'll have the x squared plus 1, times the derivative with respect to x of the g1, which is going to be x cubed. Okay, so now we set it up, and now we can take the derivatives. So this is going to be x cubed times, and now taking this derivative, we know that that's going to be equal to 2x to the power of 1, and then there's a 0 there, plus, now we leave this one alone, x squared plus 1, and then the derivative of this is going to be equal to 3x squared. Good. So we're basically done with the derivative at this point. It's just a matter of simplifying, combining like terms. Okay, so then if we multiply these, we get 2x to the power of 4 plus, and now if we distribute these, we get 3x to the power of 4 plus 3x squared. And then combining those two, they have the same power of 4. We get that the derivative with respect to x is equal to 5x to the 4th power plus 3x to the 2nd power. Okay, so here's our answer. And let's confirm that it matches what we got the first time. Right, so it matches exactly what we got the first time, right? So the first time we did it by first distributing, simplifying, and then using our power rule to find the derivative. But now we found this new process that says, okay, well, you don't have to distribute and simplify first. We can use this product rule, and the product rule ends up giving us the exact same answer. Okay, at this point, the advantage of using this product rule is still not very apparent. You know, okay, we got the same answer doing it both ways, so who cares? But now let's do a more complicated one where the advantage starts to make a little bit more sense. Okay, so given this function, f of x equals to x to the 3rd minus 2x to the 4th times 6x to the 3rd plus 2e to the x power. find the first derivative and find the second derivative. Okay, we start to see that, okay, it's going to be a pain. You could still FOIL this whole thing out, get a polynomial of 4 terms, and then find the derivative of each one. Okay, it's still not terrible to do it this way. But where we're heading soon is that not only are we going to have things that look like this, but soon there might even be a power here. Like maybe this is 6x to the third power plus 4 e to the x, and the whole thing is raised to the fourth power. Well, that's going to be ugly, right? If we have to FOIL this whole thing out, we already know this is just going to be one crazy, long, ugly mess. And if you're not allowed to use technology, just figuring out the product of that could take you like half an hour. Plus, it would be long and messy and leave a lot of room for making small arithmetic mistakes. So there's like a really good chance that at the end of the rainbow, you still get the wrong answer. So that's not fun. So we want to come up with a way, or we want to be able to use the product rule so that we don't have to simplify, multiply, and distribute first, that we can just jump right into finding the derivative and hopefully avoiding a lot of that heavy lifting. Okay, this is where we're heading. However, in order to be able to do this particular one where there's an extra power there, we still need one more rule, which we haven't learned. So I'm going to go ahead and erase this 4 for now. And I was just giving you like a preview of exciting things to come. Coming to a math lecture near you soon enough is going to be something that has a power there. But for now, we'll stick to something that looks like this. And even without that 4, this is pretty ugly, right? So we want to use our product rule. Let's use our product rule to figure this out. Now, just like before, I'm going to go ahead and label these just so we can follow the rule. But we won't always do that. So I don't know, let's label this h of x, and let's label this v of x, just to get used to different variables. So based on that, I could say that, okay, f of x could be thought of as h of x times v of x. And according to our product rule, that means that the first derivative of x is equal to h prime. And just to get used to a different notation, let's get rid of the of x, right? That's another common notational style for us to leave off the x. So the first derivative would then be f prime is equal to h prime v plus hv prime, right? Do you see how it's nice and smooth? I can see why there's an appeal to move to this kind of notation, right? It's so smooth and slick. But the drawback is that if you don't know what you're talking about, then it leaves room for people to misunderstand what this means and get confused. But I think we're at the point where we can see this and make sense of it, right? This is the h function. We want the first derivative of the h function times v plus, now leave the h alone, take the first derivative of the v function. And remember, the order doesn't quite matter. We just got to take turns with this. So if somebody else says, no, I want to do v, then h prime, plus then v, plus v prime, then h, okay, that's fine. You're taking turns. Take the derivative of the h1, take the derivative of the v1, right? So there's a variety of ways in which we could do this. Okay, so let's go ahead and write it out then. So that means that that first derivative of x is equal to the derivative with respect to x of, oh, you know what? And again, just in the spirit of doing different notation styles, I'm going to do it a little bit different. I'm going to do the h, I'm just going to copy them both. So I'll do x cubed minus 2x to the fourth. Take the derivative of that, times, and then 6x cubed plus 2e to the x, plus, and now I'll copy it again, x cubed minus 2x to the fourth, times 6x to the third plus 2e to the x, and then derivative of that, right? In fact, let me highlight it. So one way to do this is just to repeat it, right? Repeat it once, repeat it twice, and then you just put the little tick mark on the first one because we need to take its derivative. Then leave the first one alone, take the little tick mark on the second one because we need the derivative of the second one. Okay, another notational style. Okay, so that first derivative then is going to be equal to the derivative of this. So that would be equal to 3x squared, right? 3x to the second power, minus, and now here we multiply the 2 and the 4 to give me 8x to the third power, put that in parentheses, times, and then leave this alone. So this would be 6x to the third power plus 2e to the x power, plus, okay, so now we got to leave the first one alone. That'll be x to the third power minus 2x to the fourth power times this thing. Okay, the derivative of this would be equal to the derivative of each one. This would be equal to times 18x to the second power. And then this one, well, we know that the derivative of e to the x is just e to the x. So this would be plus 2e to the x power. Good. Okay, so now, now that we have the first derivative, we are tasked with finding also the second derivative. Well, that's fun. We could FOIL this out again. FOIL, 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 and we'd have 4 ugly terms here, and then we'd have some ugly terms over here, and then we'd have one ginormous long polynomial, and then we can find derivatives there, that way. Or we can apply the product rule twice. Here is a product rule, here is a product rule, and then add them together. Okay, so that's what I'm going to do. So now the second derivative with respect to x is going to be equal to the derivative with respect to x of the first derivative. Right, that's how you find the second derivative, find the first derivative, and then find the derivative of the first derivative. So in fact, one way that people, textbooks might ask you a question is they might not ask you to find f prime of x. They might not ask you to find the first derivative. They might only ask you to find the second derivative. And by asking you to find the second derivative, they know that you have to find the first derivative. So it's kind of a way to kind of sneak it in there, and then it tricks a lot of people. So keep that in mind. The only way we know how to find the second derivative is to work up to it. So you got to find the first derivative first. Okay, so now how do we find the derivative of the derivative? Well, this is going to be equal to okay, so the first derivative, the derivative with respect to x of the first derivative is this whole thing. And we know that when we have terms, right, this is 2 terms being multiplied, these are 2 terms being multiplied, separated by an addition. We know we can separate this into the addition of the 2 derivatives. So that helps us simplify this into the following. Okay, so we were able to separate it into 2 separate derivatives, the derivative with respect to x of this product plus the derivative with respect to x of this product. And now we need to use our product rule here. Again, we could FOIL it all out and find the derivative that way. That's always an option. Well, it's an option in this case, but we don't want to do that. Let's do our product rule. Okay, so it's really long, so let's make sure I did this the right way. I have a product rule here. This product rule, this one right here, I expanded it out, and it's this whole thing right here all the way out there. Then I'm adding, and that addition is here. So it's one big long continuous thing. On your paper, this might be like a good way to do it. Do a little space indentation just to remind you that this is one big long addition. Okay, so we take turns, right? So it's the derivative of the first function, leave the second function alone. So just to make sure it's clear, let's wrap it up in parentheses. So this derivative applies only to this one, and then we multiply it times this thing. And now we leave the first function alone, and we multiply it times the derivative of the second one. Right, so we're taking turns with the derivatives, adding them together. And then plus the derivative of the second, we apply the product rule once again. So it's going to be the derivative of that first function times the second function plus, now leave the first function alone, times the derivative of the second function. Fun. Okay, but each one of these derivatives is not so bad. So let's figure out, let's expand this a little bit more. So this is going to be, okay, so the derivative of this one, that's just going to be equal to 6x to the first, so 6x, minus 24 x squared, parentheses, times, leave this alone, so that'll be 6x cubed plus 2 e to the x, plus, now leave this alone, that's going to be 3x squared minus 8x cubed, times, now the derivative of this is going to be 18x squared plus 2 e to the x. Right? The derivative of e to the x is just e to the x. Okay, and now down here, so now plus, so now here plus, now the derivative of this again is pretty easy. This should be 3x squared minus 8x to the third power times, leave this one alone, 18x squared plus 2e to the x plus, and now leave this one alone, that would be x cubed minus 2x to the fourth. Finally, the derivative of this last one will be equal to 36x plus 2ex. Whew. Okay, so can we simplify this? Can this be simplified? Well, this term and this term are the same, which would bring these two together. Okay, so we have four terms. We have this product here, and then this product here. And notice that these middle two turn out to be exactly the same. 3x squared minus 8x cubed times 18x squared plus 2e to the x. So this term, this whole complicated thing, and this whole complicated thing are identically the same. And there's one copy of that one, and there's one copy of that one being added, and we're adding them. So I can bring those two together and say that there are two copies of those. Okay, so here's my final response here. The second derivative with respect to x is equal to 6x minus 24x squared times 6x cubed plus 2 e to the x plus two copies of 3x squared minus 8x cubed times 18x squared plus 2 e to the x plus x cubed minus 2x to the fourth times 36x plus 2e to the x. Fun. Okay, so given that our function f of x is equal to x to the third minus 2x to the fourth times 6x to the third plus 2 e to the x, and we want to find the first and the second derivative, then this is how we do it. Our first derivative is in this red box here. Right? It's a straightforward application of our product rule. And then once we want to find a second derivative, we find the first derivative of the first derivative, the derivative of the first derivative, to give us our second derivative. And then it's this crazy long thing. And we just end up applying the product rule twice. And this is our final answer here. Okay, product rule. All right, another example. Okay, find the third derivative of y equals to 3x squared e to the x, right? So here's a multiplication. Find the third derivative. We can also, ask the same question by saying find this, find 1, 2, 3, right? Same thing, that's the third derivative. Also, notation, we also know that we could do this, put a little 3 in parentheses in the exponent. Both of these also represent the third derivative. If we go back to function notation, that's also very popular. Let's go back to rewriting this as f of x equals to 3x squared times e to the x. You can always do that even if it wasn't presented that way. And then, of course, we can say that this is 1, 2, 3 derivative, the third derivative of x. Or, again, using that little notation, we could say f3 of x. Okay, so just getting used to the various ways in which they can ask you to find derivatives. All right, so let's just start with the first derivative. We got to take the first derivative. We have to find the first derivative so we can find the second derivative so we can find the third derivative. So even though they're just asking you for one answer, find the third derivative, we can't just jump to it. We don't have a way of skipping the first two derivatives and getting to the third derivative. Not yet anyway. That's an interesting question in math, right? What would be a way to skip the first and the second derivative and jump right to the third derivative? Well, that's fun for another day. But for now, all we know how to do is skip one. All we know how to do is go in order. Okay, so the first thing we have to do is find that first derivative. Find y prime. And of course, this can be thought of as a multiplication, right? We have this function here, and we have this function there. We have two functions, so we can use our product rule once again. So it's going to be 3x squared e to the x plus 3x squared e to the x. And we're going to take the derivative of the first one, leave the second one alone, plus, now leave the first one, right? Taking turns. That's the product rule. Okay, so this is fairly easy. This is going to be equal to 6x to the first power times e to the x, plus, leave the first one alone, that'll be 3x squared, and the derivative of e to the x is just going to be e to the x. Good. Okay, so now we want the second derivative. Now we could jump to the second derivative, and just like before, we can think of this as two separate cases of the product rule. So apply the product rule here, apply the product rule there, and then do it that way. But this has a natural and very easy way to simplify this because we can factor out the e to the x. And so we could rewrite this very easily as 6x plus 3x squared times e to the x. And then we can think of this as one simple product rule rather than the addition of two separate product rules, right? So if you can simplify your way to something easier, why not do that, right? Okay, so now we can take the second derivative. So the second derivative is going to be equal to the first derivative. It's going to be equal to y prime prime, the derivative of the first derivative. So the second derivative is going to be equal to 6x plus 3x squared, parentheses, e to the x, parentheses, and we want the derivative of that whole thing. And of course, we know that's the product rule. So the second derivative is going to be equal to 6x plus 3x squared e to the x plus, and then 6x plus 3x squared times e to the x. And again, we got to take turns. So we're going to take the derivative of the first one, leave the second one alone, leave the first one alone, take the derivative of the second one. Okay, so now that, again, this should be nice, easy derivatives. So this is going to be the second derivative is equal to 6 plus 6x e to the x plus, and now leave this alone, 6x plus 3x to the second times e to the x. The derivative of e to the x is e to the x. Good. Okay, so once again, we can simplify this before we jump into our third derivative because we can easily factor out Well, we can factor out an e to the x, but we can also factor out a 3. Everything shares a 3. So let's factor out a 3. 1, 2 equals to 3e to the x gets factored out of everything. So factor out a 3 from there, we'll end up with a 2 plus 3x. Right, factoring out a, oops. Right, we'll end up with another 2 here. So factoring out a 3, we end up with a 2 plus 2x plus, now factoring out a 3, we'll end up with 2x plus x squared. And then that e to the x also gets factored out. And now this simplifies a little bit. This turns into 3e to the x, parentheses. Now nobody wants to play with this 2, but the 2x and the 2x combine, so we'll have 2 plus 4x plus x squared. So once again, we've managed to simplify it a little bit into something that's just the product of a constant e to the x times something that looks like a simple polynomial. Okay, so finding the third derivative should be no problem at all. Okay, so now the third derivative, is equal to the second derivative, and then we take the derivative of the second derivative, right? And so I just copied this down because all of this is the second derivative. Okay, so all of this is the second derivative. We want to take the next derivative. The third derivative is equal to the derivative of the second derivative. Okay, and so now this is going to be the product rule once again. Okay, so I just kind of copied them twice, and I'm going to take turns taking derivatives. It's going to be the first derivative of the first function, leave the second one alone. Now leave the first one alone, take the derivative of the second one, right? We take turns. So the third derivative is going to be equal to 3e to the x. That's the derivative of this thing. Just copy it again. And then leave this function alone. So it'll be 2 plus 4x plus x squared. Plus, now leave this function alone. That'll be the 3e to the x power times the derivative of this polynomial. The derivative of 2 is 0. The derivative of 4x is going to be a 4. And the derivative of x squared is going to be 2x. So there's our answer. Once again, I can factor out this term. They both share this and this. And that's about it. So let's factor that out. And we get that the third derivative is equal to 3e to the x power times, and then it'll be 2 plus 4x plus x squared plus 4 plus 2x. So a couple things simplify, and we get the third derivative is equal to 3e to the x plus, okay, 2 and 4 combine to give me 6. This guy and this guy combine to give me 6. And now this and this combine to give me plus 6x. Plus 6x. And finally, we get a plus x squared. So that's good enough as an answer, or if you'd like, we can distribute it and turn it into a nice pretty polynomial. The third derivative equals to 18 e to the x plus 18 x e to the x plus 3x squared e to the x. Okay, so there you go. This is how you find the, oops, gotta get an extra little tick mark over here. This is the third derivative. So you can see right away how these tick mark things become a little bit weird. The third derivative, the fourth derivative, the fifth derivative. Eventually you get so many tick marks that it becomes kind of silly trying to count how many tick marks there are there. So that's why the other style of notation like this becomes a little bit nicer. So for one derivative or two derivatives, the tick marks are very popular. But starting with 3 forward, we might want to do this notation instead. But at any rate, the third derivative equals to this guy. And then, of course, this is also a nice way to stop as well. Nice and neat factored form. Okay, moving on. Okay, so given g of x equals 2, the product of x cubed plus x e to the x times f of x, where f of 2 equals to 5 and f prime of 2 equals to negative 3, find g prime of 2. Okay, so by giving you this information and giving you that f prime of 2 equals to negative 2, it's already implied that f of x must be differentiable, right? Because a derivative exists, or at least it's differentiable at 2. And that's what we're interested in. We're interested in g prime of 2. We know this is differentiable at 2. And we were just told that f is differentiable at 2. So we can find this derivative. All right, so what we're going to do is we're going to apply our product rule, and then we'll leave the f of x in terms of f of x or f prime of x, and then we have the values of 2 over here. Okay, so let's apply it. So the g prime of x, following our product rule, it's going to be the following. Okay, so I just copied it twice because there's 2 terms, and now I got to take turns taking derivatives, so it's going to be the derivative of the first one, leave the first one alone, and now derivative of the second one. Good. All right, so now let's simplify it. G prime of x is equal to, all right, now taking the derivative of this, well, I can see I'm going to need a product rule right in there. So this, the derivative of this first one is going to be a little complicated. It's going to be the derivative with respect to x of the x cubed plus the derivative with respect to x of the x times e to the x. Right? That's that whole derivative. And when I'm done with all that whole mess, I got to multiply that by f of x. Okay? And I know I'm going to need a product rule here. Okay, plus, and now this we leave alone, x to the third power plus x e to the x times, and well, I don't know what this is, so we just leave it alone. It's f prime of x. I know it exists, at least it exists at 2, and that's where I'm interested in, right? We know it exists at 2. We are given that f prime of x exists at x equals to 2. It might not exist everywhere, but it definitely exists at 2 because it's given there, and that's all we care about. Okay, so g prime of x equals 2. Now this is easy. That's going to be equal to 3x squared, no problem, plus, and now we know we take turns. So this will be the derivative of the first one, d dx of x times e to the x, plus, leave this alone, and then d dx of e to the x. All of that gets multiplied by f of x, plus, and now there's really nothing to do here, so we just copy it. X to the third plus x e to the x f prime of x. Okay, so now this simplifies. The first derivative of x is going to be equal to 3x squared plus this derivative becomes 1, so that'll just become e to the x. Right? This just becomes 1. And the derivative of e to the x is just e to the x. So we get a plus x e to the x. And then that whole thing gets multiplied by f of x plus, and then just copy that. We get x to the third power plus x e to the x. And the whole thing gets multiplied by f prime of x. Okay, so we found the first derivative of g of x. They didn't ask for it, but of course we have to find it if we want to find f prime of 2. So now we can get on with the business of finding this. So this is going to be f prime of blank equals to 3 blank squared plus e to the blank plus blank times e to the blank. That whole thing gets multiplied by f of blank plus blank to the third plus blank e to the blank f prime of blank. Okay, and so in this case, x is equal to 2. So put a 2 there, put a 2 there, put a 2 there, 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 2 there, 2 there, and a 2 there. And we were given that f of 2 is 5, so we know that this is really equal to 5. And we were given that f prime of 2, this guy is really equal to negative 3. Like, we were never given what f of x is, but that's okay. We just needed to know what f of 2 was, and f of 2 is a 5. Likewise, we didn't know what f of x was, so we don't really know what f prime of x is, but we don't need to know it. We were just simply told that f prime of 2 is negative 3. Okay, so now we simplify, and we're almost there. So simplifying this a little bit, we get g prime of 2 is going to be equal to 3 times 4, that's going to be 12, plus e squared plus 2e squared. Together they give me 3e squared. And all of that gets multiplied by 5, plus, and now this becomes 8 plus 2e squared. And all of that gets multiplied by negative 3. So distribute and combine like terms, we end up with 12 times 5. So we end up with 60 plus 15e squared plus, and then we get negative 24 plus negative 6e squared. And then, of course, these two combine, this one and this one combine, and then the constants combine. And so my final answer is g prime of 2 equals to, combining the constants, I get 36. And combining these, I get a plus 9e squared. So there's my answer. Okay, so given g of x equals to this product, we can apply our product rule, simplify, combine, reduce, and then come back and evaluate our function defined g prime of 2. Okay, so now let's think about what this means. So we are given this function here. We can't really graph it because we don't really know what f of x is. We only know that f of 2 is 5, and we know that f prime of 2 is negative 3. So we can evaluate this function at 2. Let's do that. Okay, so just evaluating this function at 2, get g of 2 is equal to 2 to the power of 3 plus 2 times e to the power of 2 times f of 2. Okay, so we can simplify that. That means that g of 2 equals to 8 plus 2e squared. And then the whole thing gets multiplied by f of 2, which is a 5. So then we can simplify again and say that g of 2 equals to 40 plus 10e squared. Okay, so we have a value of g of 2, and we have g prime of 2. Okay, let's use a calculator to approximate these and get a decimal approximation to these values. Okay, so first I'll calculate this. So let's do e squared times 10 plus 40. So I get this, 113.89. 113.89. So I have the ordered pair 2 comma 113.89. And now this, let's approximate the derivative at 1. It is e to the power of 2, enter, times 9, enter, plus 36. So it's 102.5, let's say. Okay, how do we interpret these two numbers? Just to draw something, just to give us a sense, an idea of what's happening, let's draw the following. So we're going to draw the graph of g of x. Now I have no idea what it looks like, and we can't know what it looks like because I don't know what f of x is. So I can't even go to Desmos and actually draw it. So I'm just going to draw something. I don't know what it is. I'm just going to draw something. I don't know, something like that. Why not? We'll call this g of x, just to have a picture of something. Okay, now according to this, when x equals to 2, let's say 2 is right here. Let's say 2 is there, why not? That's 2. Then the output value, well, okay, well, this isn't a very accurate scale, perhaps. That's okay. We're just drawing a sketch here. So this is going to be the point 2 comma 113.89. That is this point right there. So this comes across this way, and it's at 113.89. And if we draw the line which is tangent at this point, say maybe this one, then the slope of this line, tangent to g of x at point, let's just call it 2 comma g of 2. The slope is m equals to 102.5. Okay, so it would be much steeper, right? If the slope is 102.5, it would be a very steep positive slope, but you know, this does the picture. Gives you some sense, right? So this 102.5 is the angle, the slope of the line tangent to the function g of x at x equals to 2. Okay, given f of x equals to this division, 5 plus x squared divided by x to the third power, find f prime of x. Okay, so one thing we could definitely do is to separate these. We can simplify these and separate it as 5 over x to the third power plus x squared over x to the third power, right? And then that easily simplifies as being 5x to the negative third power plus, and then these reduce, and we end up with 1 over x, which is the same thing as x to the negative 1 power. And now when we want to find the derivative, f prime of x, that's easy. The derivative with respect to x of this thing is 5x to the negative 3 plus x to the negative 1. So this is going to be negative 15x to the minus 3 minus 1. Remember, we subtract 1 from the exponent. In this case, we're going to go deeper into the negatives. Don't make the mistake of thinking this answer is negative 2. It's going to be negative 4. We go deeper into the negatives. We subtract 1. Bringing down that minus, we end up with a minus 1 times x to the minus 1 minus 1. Again, we go deeper into the negatives. Like that. Okay, and so f double f prime equals to negative 15 x to the minus 4 minus x to the minus 2. And then going back to this style, we could say that this is then equal to minus 15 over x to the fourth power minus 1 over x to the second power. And then just to bring it all together into one big happy fraction, we could multiply that by x squared, multiply that by x squared, get a common denominator of x to the fourth power. And so we would conclude that the derivative is equal to negative 15 minus x squared all over x to the sixth power. Okay, a perfectly good way to do it. Perfectly great way to do it. However, we're going to explore two different ways of doing it for the same reason as before. Right now, we were able to simplify this crazy division into an addition of two fractions, and then those fractions were pretty easy. But we are going to be moving forward with cases, with situations where that might not be so easy. Okay, so the first thing I want to practice is rewriting this as a multiplication and finding the answer using our product rule. So I'll put a big giant OR here. Or another perfectly good way of doing it is the following way. So we could say that instead of thinking of our f of x function like this, we could say that f of x is actually equal to 5 plus x squared times x to the negative 3. And so now we have a multiplication. So we can use our product rule. So now let's apply our product rule. The derivative then is equal to, remember we copy this twice, 5 plus x squared times x to the negative 3 plus 5 plus x squared times x to the negative 3. And then we're going to kind of take turns taking derivatives. So that'll be that derivative, leave the second one alone. Now leave the first one alone, take the derivative of the second one. Okay, so now the derivative with respect to x is going to be equal to, this is easy, derivative of 5 is 0, and the derivative of this is going to be equal to 2x. Leave that second one alone, so that'll be times x to the negative 3 power. Plus, now we leave this one alone, and that'll be 5 plus x to the second power. And the derivative of this is going to be negative 3 x to the negative 3 minus 1. Remember, we go deeper into the negatives. Minus 1 in the exponent. Okay, so now all we have to do is simplify. This becomes, okay, so we can think of adding the exponents. So this becomes 2x to the minus 2 power. Plus, this becomes 5 plus x squared minus 3x to the minus 4 power. And then we're going to distribute. Okay, f prime of x equals to 2x to the minus 2 power plus 5x, When we distribute, we end up with a minus 15. Minus 15 x to the negative 4 power minus 3 x to the minus 2 power. Right? We add these exponents. Positive 2 plus negative 4 gives me a negative 2. Good. And now we can combine these two. This one and this one have the same powers. So we can combine them to be equal to minus 1. So we get f prime of x equals to minus 1, so minus x to the minus 2 power, minus 15x to the minus 4 power. Okay, so then let's rewrite it. This becomes f prime of x equals to minus 1 over x squared minus 15 over x to the fourth. Again, we get nice common denominator of x squared over x squared, which then gives me x squared minus 15. So this becomes f prime of x becomes minus x squared minus 15 all over x to the fourth power. And okay, well, if I just flip it around, it'll make it look exactly like his neighbor across the way. Just to make them look exactly the same, I could say that this is minus 15 minus x squared all over x to the fourth. Oh, oops, a little mistake over here. This was x to the fourth. I don't know why I got an x to the sixth. So correction over here. This was x to the fourth. And that matches this one. X to the fourth. Okay, so what we have here is a case where we were first given this division, right? This rational function. We wanted to find the derivative of this rational function. It just so happened that this particular case was a case where the fraction could be separated this way, simplified, and then we can find the derivative this way. Or we can rewrite it and write it this way. So now we can think of it as a multiplication and then be able to find it this way. So we have two really good ways of finding the answer. But we want to develop a third way of finding the answer, because moving forward, we're going to run into cases where it's not so easy to simplify the fraction. We can't just kind of get rid of the fraction in a very easy way. For example, what if the original one wasn't this one, but it was this? Plus x squared divided by x cubed plus 7. Now it's not as easy to separate it into two separate fractions. I mean, we could do that, but then we'd have some ugly things anyway, right? We could separate it and get 5 over x cubed plus 7 plus x squared over x cubed plus 7, but that didn't necessarily make it easier. Now we have something ugly over here, and I don't even know how to simplify that, right? So we can't just ignore the fraction. So what we want to do is develop a rule that allows us to find the derivative of a rational function by doing something with the numerator and denominator, kind of like what we did with the product rule. Okay, so let's present what it is. I'll show you what the boxed up rule is from your textbook. Again, I'm not going to present the theorem for it or the proof of it. We're just going to learn it, apply it, and move on with our lives. Okay, so here is what that rule is. Okay, so this is the quotient rule. If f and g are differentiable, then the derivative with respect to x of a division of f divided by g is equal to g of x times the derivative with respect to x of f of x minus f of x times the derivative of g of x all over g of x squared. Okay, so pay attention to the order of things. They're important. You have to do them in this order. So what we have is we're going to be using this rule when you want to find the derivative of a rational function, a fractional function. You have a numerator, you have a denominator, and both the numerator is differentiable, the denominator is differentiable. So we get to kind of treat them separately and then piece them together. And that's what makes this a very useful, very, very useful rule, the quotient rule. Okay, now remember the order. We have to, in the numerator, we're going to start off with the g of x, the one in the bottom. So it's bottom derivative of the top minus top derivative of the bottom. I know I'm using top and bottom, but I think you know what I mean. Numerator, denominator, all over the denominator squared. Okay, so this is a very famous property, very famous rule, kind of like the quadratic formula. It's just very common, very useful. We use it all the time, and it's this long formula people have to remember. So for that reason, there's cute little songs and stuff out there that people have created to remember this rule. Now, I can't sing it all, so I'm not going to punish you that way, but I have YouTube, so let me find someone that does a nice little song. Keep in mind that in the songs, they usually refer to low as in the denominator, and then d of high, so low, so this means the g of x is the low, d high, so derivative of the high one, minus high d low over the denominator squared we go. Right, so that kind of language is going to be happening in the song, so you just be aware of it. So for the song purposes, they refer to the numerator as the high and the denominator as the low. I guess it's high, not high. So the high and the low, and then d, when they refer to d, is equal to the derivative. Okay, so here we go.
Low D high minus high D low, all over low squared. Use a f of x over g of x. It's the quotient rule with a low D high here and a high D low there. Low D high D low, all over low squared. Low D high minus high D low, all over low squared. Use a f of x over g of x. It's the quotient rule.
Okay, and this guy's my hero.
You wake up in the middle of the night, sit up straight, and you turn on the light. What's that song? It's stuck in your head. What's that one about the quotient rule? And this is what it said. Low D high minus high D low. Over the denominator square we go. So you see a fraction that might be a clue. To take the derivative, use the quotient rule. If it doesn't rhyme, it's probably wrong. All you have to do is memorize this song. Low D high minus high D low. Over the denominator square we go. Helping Blattner and your boss. They're not as cool as Kristen But if you wanna pass this class, you had better bust your ass and toes. Low D high minus high D low. Over the denominator square we go.
All right, so that was my wedding song, believe it or not. All right, remember the formula, if we run into a fraction, a rational function like this, is going to be to think of it as low D high minus high D low over the denominator, which is again that low. The song says denominator. Over the denom squared we go. Okay, low D high minus high D low over the denominator squared we go, where the low means the G and the high means the F. Okay, it's got to be in this order, so if you do it in a slightly different order, you're going to get the wrong answer. Low D high minus high D low over the denominator squared we go. Okay, so now that we have the quotient rule, we can apply it. So let's apply it to the problem I just did, and we'll have a third way of solving it, and we'll see that they all match. And then we'll do more complicated questions involving an ugly-looking fraction where the quotient rule is really your only way to solve it. Okay, so back to this same question that we've already solved twice. We're going to solve it a third time. We have this fraction right here, this rational function. We solved it first by breaking it up into an addition of two separate fractions. Each one was very easy to simplify, and then we can use our good old power rule to find the answer. The other way we did it is to rewrite it using some clever algebra to rewrite this as a product, and then we use the product rule to give us the exact same answer. So now, just for fun, let's do it a third way. Now that we are armed with the quotient rule, we know that we can use that as well. So I'm going to use the quotient rule over here. So let's call this, here, let me zoom in. Say this one is by the product rule. Whereas over here, we're going to use the quotient rule. Okay, so this was the original function, 5 plus x squared in the numerator divided by x cubed in the denominator. So now using the quotient rule, we know that the derivative is going to be equal to this giant fraction. And now it's low d high minus high d low all over the denominator squared. Okay, low d high minus high d low over the denominator squared we go. Okay, that's about as close to singing it as I can get. Okay, so now we just simplify it. We got to take this derivative, we got to take that derivative, simplify, reduce, cancel as best we can. So we end up with x to the third power times the derivative of this is easy. The derivative of 5 is 0. The derivative of this guy is going to be 2x minus, and now leave this alone, 5 plus x squared times, and now the derivative of this is going to be equal to 3x squared divided by x to the power of 6. Okay, so now we have to be careful because this minus applies to everything over here. So be careful not to just include it to the 5, minus 5. It's going to be minus this term and then also this term. And we also have to distribute the 3x squared. So this needs to be distributed there, and this needs to be distributed there. Okay, so the first derivative then is equal to 2x to the fourth power, and then minus, and then 5 times 3 makes it 15x squared, so it's minus 15x squared minus 3x to the fourth, 3x to the fourth power. All of that gets divided by x to the sixth power. Okay, and now combining these two, this and this get to combine. 2 minus 3 gives you minus 1. So you get f prime of x equals to minus x to the power of 4 minus 15x squared all over x to the sixth power. And now we can factor out an x squared from the numerator. And just to make it look like that, I'm also going to flip them around. So I'm going to put x squared, parentheses, and then I'm going to flip these around and have a minus 15 minus x squared, right? And then the whole thing gets divided by x to the sixth power. And I just flip them around just to make it look like the other ones, just so that they all match. And now this will reduce with that to give me 4. And so my final answer will be that the first derivative is equal to this fraction, with minus 15 minus x squared all over x to the power of 4. Okay, so let's zoom out and take a look at all of them. Okay, so here we go. We have 3 different ways of solving this particular question. We were given this rational function, f of x equals to 5 plus x squared divided by x to the power of 3. And we have 3 different ways to solve this one. We separated into 2 separate fractions for the first one. So over here we separated it into 2 separate fractions, and then each one of those simplified. We can use our power rule. So that's a perfectly good way to do it. Another way is to convert it into the product rule and use that. And then now we have the quotient rule, 3 different ways. Now, do we need all 3 different ways? Well, it's always nice to have options. In this particular question, well, I should say in all questions, you should just do whatever is easiest for you. Some questions, some functions naturally lend themselves toward one method. The way they're presented or the actual, the actual equation you have to deal with, it might be easier to separate it, right? Why do something super complicated when maybe it just simplifies really easily like this one does? So, why bother with the really complicated ones? If it simplifies, make it simple and do it that way. But as we will see, there are many cases where you really can't simplify it this way, and your only way to find the derivative is to either use the product rule or the quotient rule. Okay, so let's do an example where this is just not really a feasible option, and we'd rather do either the product rule or the quotient rule. Let's say that g of x is equal to this nasty rational function. This is not something that can be easily simplified into a sum of things that we can then use the power rule, like we did like we saw in the previous example. So this isn't great. Now we could use the product rule if we think of it this way. We could say, well, that means that g of x is equal to 3x to the 4th power minus 2x squared plus 10 times, and then remember this whole thing can be thought of as being raised to the power of 1 as a unit. The whole thing is to the power of 1. So then we can take that and move it to the numerator and do x to the power of 3 minus 6x squared to the power of minus 1. And so that helps us rewrite it as a product. However, then that means we have to deal with this. How do we deal with that? We haven't gotten to a point where we know how to deal with that. That requires another rule we haven't learned yet. So we don't want to do it this way yet, but we can, and we will be able to do that soon, but not yet. So for the moment, this question, g of x, there really isn't a very good way to do it other than the quotient rule. This is exactly the type of situation where the quotient rule is going to be super helpful. Okay, so let me erase this because we don't want to deal with this right now. Okay, so now let's find the derivative using the quotient rule. So that means that g prime of x is going to be equal to this big fraction. The bottom part's easy. That's going to be x cubed minus 6x squared. And then the numerator, remember it's low d high, so it's going to be x cubed minus 6x squared. D high, derivative of the numerator, 3x to the 4th minus 2x squared plus 10, minus high, that would be 3x to the 4th power minus 2x squared plus 10. So low d high minus high d low. Now that's all that's left. Derivative of x cubed minus 6x squared. Okay, so now we just have to find a couple of derivatives. I'm going to just put them right here. The derivative of this guy, very easy. It's just a polynomial. It's going to be the derivative of each one of these terms. So this becomes 12x to the 3rd power minus 4x, and that's a 0. Derivative of 10 is 0. And the derivative of this guy is super easy as well. That's just going to be equal to 3x squared minus 12x. That's the derivative of that. So now we can just copy the whole thing. G prime of x is equal to x cubed minus 6x squared times 12x cubed minus 4x minus, and now this guy becomes 3x to the fourth minus 2x squared plus 10 times, and now this guy becomes 3x squared minus 12x divided by, and now this x cubed minus 6x squared, and then the whole thing gets squared. Now I think this is a pretty good place to stop. So read the instructions and see what what they ask you to do. We could FOIL it and simplify it a little bit more, and we could factor this out and simplify it a little bit more there. But I'm not sure that we're going to get that much more out of it. So I would be happy to stop here. But just for the sake of completion here, let's just see what it would look like if we kept going. Okay, so if we kept going, I'm going to have to FOIL this out here. I'm going to put it in here just to... Okay, so this one would be 12x to the 6th power minus 4x to the 4th power minus 72x to the 5th power plus 24x to the 3rd power minus, and now just to be careful, this minus is going to apply to the whole thing. So I'll put parentheses there. And this will be 9x to the 6th, 9x to the 6th power minus 36x to the 5th power minus 6x to the 4th power plus 24x to the 3rd power plus 30 plus 30x squared minus 120x. Let's put that in parentheses. X equals to this, and then that whole thing gets divided by the product of these two. So again, you could FOIL it all out, and we'd end up with x to the 6th power minus 12x to the 5th power plus 36x to the 4th power, if you FOIL this out. And then we can combine some like terms. Let's see. X to the 6th power, that would be this guy and this guy. Remember, that's going to be minus 9. So this would be equal to minus 9x to the 6th power, taking care of the x to the 6th powers. Now taking care of the x to the 5th powers, there's the minus 72 minus 36. So minus minus becomes plus. So it's going to be minus 72 plus 36 gives you minus 36x to the 5th power. So that takes care of this guy and this guy, and we already took care of this guy and that guy. Okay, x to the 4th powers, we got this guy here. We got this term of minus 4, and then minus minus becomes plus 6. So minus 4 plus 6 becomes plus, minus 4 plus 6 becomes plus 2. Okay, and that takes care of this term and that term. Now minus 24 plus 24, those just cancel. Minus a positive 24x to the 3rd power minus 24x to the 3rd power, and that takes care of all those terms. So now we just subtract. So then we get minus 30x squared plus 120x, and all of that gets divided by x to the 6th power minus 12 x to the 5th power plus 36x to the 4th power g prime of x. Okay, so this is an alternative version over here, just expanding the whole thing out. Okay, so personally, I think that this red box solution is good enough because at that point, you've already applied the quotient rule and you found the derivative. And then to go from that red box solution to this blue box solution, it's just this whole foiling and canceling and reducing, and it's super easy to make a mistake somewhere. I'm not even 100% sure my answer is right. I didn't really, pay close attention. So it's entirely possible I'm off by a sign somewhere and the whole thing's off. So I prefer the red box. It's a good answer, and it helps us. In many cases, it's good enough just to find it in this format. In some cases, we might have to keep going. So for example, if you're asked to find the second derivative of g, well, it would be hard to move forward to the second derivative with this one because we have to apply this quotient rule again, low d high minus high d low. And if the high is already this complicated thing, it makes it more work to find the derivative. So in a case like that, it might be worth the trouble to very carefully expand it all out so that therefore for the second derivative, we apply it to this one. And now finding the derivative of the numerator is pretty easy. That's just a polynomial, and we know finding derivatives of polynomials is always super easy. So if you're asked to find the second derivative, it might be worth the trouble. Also, if you're checking your solutions against something, back of the book or something like that, then you might find it in expanded form like that instead of this. So you need to know how to expand it all out just so you can check it against your solutions. Also, your next calculus instructor might not like for you to stop there. They might say, make sure you expand out all your solutions, FOIL, distribute, combine like terms. So they might be interested in seeing it that way. For me, I just would hate to have to dock you points on a test because you forgot to distribute a minus somewhere. That just seems like a silly algebra mistake, and we're trying to focus on evaluating your capacity to do calculus, not your capacity to do basic arithmetic and algebra. Although, there is going to be, one is supportive of the other. So in some way, your algebra skills and arithmetic skills do play into your calculus evaluation. But, I feel like this is a little too heavy-handed for that. Okay. Also, I didn't ask for this, but note that another nice little extension to this question might ask you to find the derivative at a particular point. So we could say that this is part A, find the derivative, and then maybe part B, a cute little part B could say find g prime of 1. Right? And we could see that all we have to do is evaluate this and put a 1 everywhere we see an x. And so in a case like this, we see that this is good enough. There's no real reason to expand it all out and go through this painful step to get it to this, when all you need to do is find g prime of 1, or even better, it might be g prime of 0. But remember, if we put a 0 in there, we might be dividing by 0. So we got to be careful, never divide by 0, and that includes this quotient rule. Okay, all right, so let's say that they ask you to find g prime of 1. Okay, so let's say we're asked to find, as a part B, find g prime of 1. Okay, so I'm just going to copy this guy, leaving blanks. Okay, so I copied this term here. This is just this part up here. And now minus, and then this part over here. And I just created this little, I broke it down like this, because otherwise it would extend out that way and I wouldn't be able to put it on a nice screen. It would get, the font would get too small and stuff. stuff. So on your own paper, it's another nice little technique to do a little indentation to show that one big line can be written this way. Okay, so I just copied this one onto there, and now I'm going to replace 1. Let's say that here is a 1. So it's 1 cubed minus 6 times 1 squared times 12 times 1 to the power of 3 minus 4 times 1 minus 3 times 1 to the 4th power minus 2 times 1 to the 2nd power plus 10 times 3 times 1 minus 12 times 1, all of it divided by 1 to the 3rd power minus 6 times 1 squared, the whole thing raised to the power of 2. Okay. So now we can simplify that a little bit. That's going to be 1 squared minus, 1 cubed, that's just 1. 1 minus, this is really just 1 minus 6, which is going to be negative 5. And this is going to be 12 minus 4, which is 8. Okay, so I get 1 minus 6 gives you negative 5. So this would be negative 5 times 8 minus, and then here I end up with 3 minus 2, which gives you a 1, plus 10 gives you an 11. 11 times, and then this is 3 minus 12 gives you a negative 9. All of that gets divided by 1 minus 6, which gives you a negative 5 squared. Negative 5 squared. Okay, so this g prime of 1 is equal to negative 40 plus 99 divided by 25, which gives you g prime of 1 is equal to positive 59 divided by 25. Okay, we can also just turn that into a decimal to get a better sense. It's a little bit more than 2, right? It's 2 9/5. So let's erase this over here, I guess. 2.36 equals to 2.36. Okay. So let's confirm what that means, or let's think about what that means. Here is our g of x function. If we graphed it, and then we found a point on this graph that corresponds to an input value of 1. Okay, so if we put 1, it's a good idea. Let's just put 1 here. Let's find g of 1. I'll put it in green. G of 1 is equal to 3 times 1 to the 4th power minus 2 times 1 to the 2nd power plus 10 divided by 1 to the 3rd power minus 6 times 1 squared. So that's just going to be 1. 1 to the 4th is 1 times 3. That's just going to be 3 minus 2 plus 10 divided by 1 minus 6. That's going to be 3 minus 2. That's equal to 1 plus 10 makes it 11 divided by negative 5. And negative 5 goes into 11 twice with 1 remaining. So this is going to be negative 2.20. Okay? So here is our function, g of x. I don't know what it looks like, but it's some function, g of x. I know that one ordered pair on this function is the ordered pair 1, negative 2.20. That's a point on this function. And if I wanted to find the slope of the line tangent at that point, here it is. 2.36 is the slope of the line tangent to this point on the function. Good. All right, let's move on. Okay, find the equation of the line tangent to the function f of x. F of x equals to x times e to the x all over 1 minus 3 x to the third power when x equals to 1. Okay, so we're going to need an ordered pair, a point on our function. So we're going to have to evaluate this function at 1. So let's just start there. So f of 1 is going to be equal to blank e to the blank all over 1 minus 3 blank to the power of 3. Sorry. Okay, so we're going to put a 1 for our input. So put a 1 there, put a 1 there, put a 1 there. And so we get that f of 1 equals to e in the numerator, just e, divided by, and this is going to be 1, this is going to be 1 minus 3 is going to be minus 2. Okay. All right, so then that means that our ordered pair, this could also be rewritten as negative 1/2 e. So our ordered pair is going to be 1, comma, negative 1/2 e. That's fine, or we can turn it into a decimal. Let's find the decimal approximation. Clear? Negative 0.5 times e. So that's negative 1.3591. 3591. Okay, but it's good enough to leave it like this, right? Why round? I mean, if you need to get like a visual sense of how much this is, it's kind of hard to say half of e. But, you know, remember, e is approximately 2.718, so that should help. But if you need to get a better approximation, a better sense of what number that is, then okay, you would convert it into a decimal approximation. But this is still superior. This is still better because you have an exact answer. So why not just leave it as half of e? Okay, so we have our ordered pair. Now we are tasked with finding the equation of the line tangent to this point, which means we have to find the slope of that line, which means we have to find the derivative of this function. Okay, so let's use our quotient rule. Right, it's clear that the quotient rule is really best fit for this situation. Right, there's really no way to break this down into something that we could use the power rule, like we did with the very first rational function. And I could rewrite this as a product, but then I'd have this whole denominator to the power of -1, and we still haven't learned how to deal with that yet. So quotient rule is our best option. Okay, so we know it's going to be that the derivative is equal to, and it's going to be this very nasty fraction where we have low d high minus high d low over the denominator squared we go. Okay, so when I say low, I'm referring to the denominator, right? Low. Here's what I'm talking about when I say high. So low d high minus high d low over the denominator squared we go. Okay, so now we just have to simplify this. Luckily, oh, wait a minute. This is going to be a product rule right here. Right? We have a product rule right there. This one's a very easy denominator. This one's not quite as easy, but it's really not that bad. So I'm just going to squeeze it right above here. let's see, this is going to be a product rule. So it's going to be equal to, let's put it in green, it's going to be x e to the x plus x e to the x. And now I need to take the derivative of the first one, then leave the first one alone, take derivative of the second one. Okay, but the derivative of the first one, the derivative of x is just 1. So this just becomes e to the x. Well, I'll just put the space in there. This just becomes 1 times e to the x. And now we leave the x alone, and then the derivative of e to the x is just e to the x. So that doesn't change. So the derivative of this is just going to be equal to e to the x plus x e to the x. Okay, so f prime of x is equal to a giant fraction. We're going to leave this alone. This will be 1 minus 3x to the third power times the derivative of this, which we just discovered is this. So that'll be e to the x plus x e to the x minus, now we leave this term alone, that's x e to the x, times the derivative of this guy. Okay, the derivative of this, the derivative of 1 is 0, and the derivative of this is going to be minus 9x to the second power. And now the denominator squared. 1 minus 3x to the third raised to the power of 2. There it is. There's my derivative. Of course, it's really messy, and we could simplify the whole thing down. FOIL, combine like terms, reduce, cancel, till our heart's delight. Really apply all those awesome algebra skills. But they would be kind of wasted here because we don't really need them. All we need to do is figure out the derivative at 1. So we could just evaluate this at 1 and not bother with simplifying it. So let's find out what that is. It's going to be the derivative evaluated at, and it's going to be this giant fraction, 1 minus 3 blank to the third power times e to the blank plus blank e to the blank minus blank e to the blank times negative 9 blank squared, all over 1 minus 3 blank cubed, and then the whole thing raised to the power of 2. Okay, and so we want to evaluate this whole thing at 1. So there's a 1 there, 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 1, 1, 1, and 1. Okay, so then luckily some stuff's going to reduce, cancel nicely. F prime of 1 is now equal to, okay, so we get 1 minus 3 times 1 cubed. That's going to be 1 minus 3. That's negative 2. Times, and then e to the first power is just e, plus 1 times e to the first power is just e to the first power. So just e. So we really just have 2e. 2e to the first power, which is 2e, minus, and then 1 times e to the first is just going to be e, times negative 9 times 1 squared is just negative 9. So we just put a plus 9 there. And then the whole thing gets divided by 1 minus 3 times 1 cubed. That's just going to be 1. 1 minus 3 is negative 2. Negative 2 squared. So then this becomes, f prime of 1 becomes minus 4e plus 9e divided by positive 4 now. And minus 4e plus 9e becomes positive 5e. Divided by 4. So it's really equal to 5/4 e. 5/4 e. Or this becomes 1.25, 1.25 e. Okay, so again, we can use our calculator to approximate that if we want to, or we can leave it alone, leave it like that. So 1.25 times e. $39.78. 3.3979-ish, approximately, rounding off. Okay, so we're almost there. Let's get back to the original question, though. The original question said, find the equation of the line that's tangent. And so far, we have found two things. We have found a point that's on the line, and we have found the slope of the line tangent at that point. So we bring those two things together to give us our final answer. So we know that there's a point, 1, comma, negative 1/2 e. And we have that slope of that line has to be equal to 5/4 e. Okay, so now we use our equation for a line. So it's y minus y given. So we have some y that's given equals to m that's going to be given, x minus some other given point. Right, so by that little notation, I mean that we have to have a point. So we're going to consider this right here as our x sub g. It's the given point, and then this is the y sub g, the given point, and here's our m. So we just evaluate this. So y minus negative 1/2 e, that's the y, equals to 5/4 e, x minus 1. Okay, so plugging in our y, plugging in our x, and now we just distribute, combine, simplify, and solve for y. We get y plus 1/2 e equals to, multiplying these two, we get 5/4 e times x minus 5/4 e. Bringing this over to the other side, we get y equals to 5/4 e x minus 5/4 e minus 1/2 e. So we need a common denominator. Let's make it that 4. So we multiply this numerator and denominator by a 2. X minus, so we'll end up with a minus 5 minus 2 gives you a minus 7/4 e. And that's the equation of our line. Okay, so we were given a rational function and we're asked to find the equation of the line tangent to the function when x equals to 1. So we first of all need to evaluate our function at x equals to 1 to figure out the ordered pair that's on our function. We did that here. That's how we got this point. That's how we get this point at 1 comma that's how we get this point, which is 1 comma negative 1/2 e. Next, we need to find the slope of the line tangent. So we take its derivative. We use our quotient rule. Low d high minus high d low over the denominator squared we go. We're careful about our derivatives. We don't need to simplify too much after that because we want to evaluate this at 1 and makes it simpler to just evaluate it at 1 rather than use our algebra to FOIL, combine, like terms. But if you want to do that, that'll work too. Okay, so we found out that our f prime of 1 is equal to this, 5/4 e. So that's the slope of the line tangent at our point. So armed with both a point on the curvature that's also going to be on the line tangent, as well as the slope of the line that's tangent, we can use our traditional formula for a line to find the equation of the line. Okay, so here's our final answer. And let's graph it and confirm with Desmos. Okay, so here in Desmos, I typed in our equation. So here it is in this blue. Right, so it looks like it's got a horizontal asymptote whenever this turns into a 0. Okay, when the denominator equals a 0. All right, but we're interested in the point 1 comma, so let's graph that. 1 comma negative 1/2. Negative 1/2 e. Okay, good. So it is on there. And then if we approximate it, it is negative 1.3591, I think we got. Okay, so that's the point we're interested in. And we're looking for the equation of the line that's tangent at that point. So after a bunch of work, we found that that equation was y equals 2, and it's 5/4, 5 divided by 4, e, x. So 5/4 e, that's just some number, right? That's the slope of our line, x. So it's got this angle here in red, but right now it's crossing through the point 0, 0. We got to squeeze it over until it crosses through a point on the y-axis such that it also goes through this point. And after a bunch of work, we saw that that had to be the point minus 7 divided by 4 e. There it is. Okay, so here is a point on my curvature, and this red one here is the tangent line, and here's the equation of the line tangent at that point. Okay, so the equation in blue was the function f of x equals to x e to the x all over 1 minus 3x cubed. This point right here corresponds, this thing is the same thing as the point 1 comma negative 1/2 e. That's an approximation, so we get this point right there. And then we find that the equation of this line is y equals to 5/4 e x. Remember, this whole thing here, including the e, is the constant. It's the coefficient in front of the x, minus 7/4 e. Okay, so that's the equation of the line tangent. Equation of line tangent to function f of x equals to x e to the x all over 1 minus 3x cubed at point 1 comma negative 1/2 e. Right, that's the full definition, description of what that red line is. And of course, it's got slope equal to, just to be super clear, it's got slope m equal to the 5/4 e, that's the slope. And the y-intercept is this thing, which is going to be somewhere over here. So that is the y-intercept, which is the ordered pair 0 comma negative 7/4 e. Y-intercept. Okay, I think that's all and everything we can identify that's relevant and important. Notice that interesting questions, there wasn't a question that was asked here, but an interesting question that we're going to have to face soon, or something you might see in your homework, is when will the tangent line be horizontal, right, or parallel to the x-axis? So notice that just kind of by eyeballing it, it seems like somewhere around here. It looks like somewhere around there we're going to have a horizontal tangent line, as well as somewhere around here-ish, just kind of eyeballing it. it seems like somewhere around there will be horizontal lines. Keep that in mind because that's a very popular question to ask. Figure out when will the tangent lines be horizontal. And also, keep in mind they might ask you something like, determine the portion of the number line, determine the segment of the domain where the derivative is always, I don't know, positive. When will the derivative always be positive? So notice that this slope here, when will the derivative be positive, which is the same thing as saying, when will the slopes of the tangent lines be positive? So here is one of them. And so if you think about when those tangent lines will be positive, if we move over here, a tangent line over here, a tangent line over there will be negative, right? When will the derivatives be positive? Okay, so we're not quite ready to be able to answer those questions yet, but that's where we're heading, to be able to answer questions like that. Identify the segment of the domain of our function f of x where the derivative is always positive, where the derivative is always negative. So prepare for those questions down the road. But for now, we're not quite ready for those yet. But this kind of a question, find the equation of the line tangent to a particular point, that's a classic question from this section. And it makes a fantastic test question now that I think about it. So make sure that you understand it. Okay, so that should be more than enough to tackle your homework. Let me know if you have any questions.